In a linear function, no variable is raised to the power other than 1. Any linear function can be written in the form of f of x equals mx plus b. And you may have seen this before in the form of y equals mx plus b in Algebra 1. So it's actually saying the same thing. There are other reasons why a function may not be linear, but the one that we're really going to focus on in this section is that there cannot be any exponents other than a 1 to make it, or for it to stay a linear function. Linear functions can be represented by linear equations, which can be written in the form of ax plus by equals c. The reason they're called linear equations is because linear equations are straight lines. That's what the graphs look like. Also notice on ax plus by equals c, there are no exponents there as well. So the opposite of a nonlinear function would be called a nonlinear function. So a function that's not linear is called a nonlinear function. That just simply means that the points on the graph do not lie in a straight line. It also means that it cannot be written in the form of f of x or y equals mx plus b. One of the first nonlinear functions that we are going to run across is called a parabola. It's the graph of a quadratic function. That's a type of nonlinear function. The main characteristic of a parabola is that it has an exponent of 2. There's actually a full chapter about quadratic equations and quadratic functions that we will see later on in this course. So the first example is to determine whether each function is linear, justify your answer. So in order to determine if it's linear, what we're going to do is we're going to try to change it to the form of f of x equals mx plus b. So on this particular first one, we have 6x minus 5 all divided by 3. So we should divide the 6x by 3 and the 5 by 3. So 6x divided by 3 is going to be just 2x. And negative 5 divided by 3, and we're going to leave this as a fraction. I like fractions better than decimals. That's going to be negative 5 thirds. Negative 5 divided by 3 is the fraction negative 5 thirds. And this is in the form of y equals mx plus b. The m is the 2, so the m is the 2, and the b is this negative 5 thirds. So since we can put it in the form of y equals mx plus b, this is linear. The way you would explain it is show that you can put it in the format of f of x equals mx plus b. So just show your work. Part b is 5y equals 4 plus 3x to the third power. And what I can immediately notice on this one is that there is an exponent of 3 right there, and linear functions do not have exponents. So this is nonlinear. And the way I can explain that it's nonlinear is that because it contains an exponent. Linear functions do not have exponents in them. Identify linear functions from a graph. Determine if these are linear or nonlinear. Basically, do they create straight lines? Is the whole graph a single straight line? Part A, you can see that it is an upside down V shape, and that is definitely not a straight line, so this is nonlinear. Part B, it does look like all of those points lie on the same straight line, and I can actually use my straight line tool to verify this. So I can start drawing here, and you can see that I can take the perfect straight line, and it covers all the points all the way to the arrow. So yes, this does appear to be a straight line, so it is a linear equation. So example number 3 is a word problem. And it says that Michaela has started working part-time at the local hardware store. Her time at work steadily increases for the first 5 weeks. Table shows her total earnings each of those weeks. Are her weekly earnings modeled by linear or nonlinear function? So what we can do on this one is we can graph it to see if the points that it creates is going to be all in a straight line. We've got some fairly large numbers here, so instead of going by ones, you can see that in the graph that's already printed off to the right, the earnings is going to go by 40s. So week 1, earnings of 85, so I would go over to week 1 and up to 85, which is roughly about, let's see, this would be 100, and then halfway between that and that would be 90, so halfway between that and that would be 85. So 85 is going to be just above the 80 on the scale that we have on here, so roughly right there. 2, 119 is going to be almost to 120. Place a point there. 3, 153, roughly right here. It's not quite to 160. 4, 187 should be slightly past halfway to 200, between 160 and 200, because halfway would be 180, so 187 would be about like that. And then 5, 221. 221 is going to be, since this would be 240 at the very top, 221 is almost exactly halfway between 200 and 240. Okay, so is this linear or is this nonlinear? And it looks to me that these points are very linear. It almost looks like they are on a straight line. I can use my straight line tool to determine that. So if I go from one point all the way up to the other point, you can see how it looks like all 5 of those points do wind up on a straight line. So that being the case, we would state that this is a linear function. Some new definitions. A point at which a graph of a function intersects an axis is called an intercept. There are 2 types of intercepts. There is the x-intercept, which is the x-coordinate of a point where the graph crosses the x-axis, and the y-intercept is the y-coordinate of a point where the graph crosses the y-axis. Most graphs do have both types of intercepts. They have an x and a y. Not all graphs have both, but many of them do have both. Example number 4 says use the graph to estimate the x and the y intercepts. So we've got a blue line, blue straight line, and it looks like it crosses right through the origin. The ordered pair of the origin is 0, 0. So it's actually crossing the x and the y axis at the same point, and for that to occur, that has to happen at the origin. So in this particular case, we would say that it does have an x and a y-intercept. It has an x-intercept. The x-intercept is at 0, and it also has a y-intercept also at 0. Example 5 is x and y intercepts of a nonlinear function. We've got lots of places where it crosses x and y axes. It's going to cross the x-axis and 3 places. It's going to cross here, highlighted in red, here. And even though it doesn't completely cross through it, it does touch it. So that counts. So it crosses or touches right there. So what are the x values of those 3 points? Notice all 3 of those points have a y value of 0. That's going to be important coming up. So the first point has an x value of -3 with a y value of 0. The second point has an x value of -1 with a y value of 0. And then the last point has an x value of 2 with a y value of 0. So the x-intercepts are going to be all 3 of those points, the x values of all 3 of those points. You have an x-intercept at -3. We have an x-intercept at -1 and an x-intercept at 2. There is one place where it crosses the y-axis. It's this point up there. It did say to estimate it, and the y-axis appears to be going by 4s, so that is the y-intercept point of, it looks like you had to go up 12 to get to that, up 12, left or right 0. Notice it has a, excuse me, I have that backwards.